Every year, more than 2 billion light bulbs are manufactured across the world. That's 60 new bulbs coming to life every second. From the glowing tungsten filaments in Edison's first incandescent bulbs to the microscopic semiconductors inside today's LEDs, the journey of artificial light has spanned more than a century of transformation. Each generation of bulbs marks a milestone in human engineering, a reminder that our quest to illuminate rooms is, in truth, an effort to brighten the future itself. In this documentary, we take you inside the fascinating process of how light bulbs are made, revealing a true masterpiece of human ingenuity and technology. If you're fascinated by manufacturing processes like this, hit that subscribe button and drop a comment below telling us what production line you'd like to see next. History of the light bulb. In 1879, Thomas Edison unveiled the first incandescent bulb capable of glowing continuously for 40 hours. Just a year later, he refined his design, extending its lifespan to over 1,200 hours and ushering in the age of electric light, a breakthrough that forever transformed human life. Have you ever wondered how different our world would look today if the light bulb had never been invented? Over time, however, this technology revealed its limits: low efficiency, excessive heat, and high energy consumption. At the dawn of the 21st century, a new revolution began as LED lighting emerged, replacing the tungsten filament with semiconductor circuits capable of emitting light without generating heat. This innovation produced brighter, longer-lasting illumination while drastically reducing power use. According to global estimates, the shift from incandescent to LED bulbs now saves more than $200 billion in electricity costs each year, the equivalent of the annual output from hundreds of thermal power plants. How incandescent bulbs are made. The journey of a light bulb begins in the glass forming section, where clear glass tubes are heated until they turn soft and flexible. This is where the bulb's neck and flared opening takes shape, marking the very first step in defining its structure. On a slowly rotating conveyor, each tube is firmly clamped between two machine heads, while gas burners surrounding it release heat reaching about 2,300 degrees Fahrenheit. As the tube spins steadily, its rim expands outward, forming the distinctive neck that will later connect to the main body of the bulb. At this stage, robotic arms hold the softened glass neck and insert a thin exhaust tube right through the center, a small channel that will later allow air to be removed and inert gas to be added. Then two fine copper wires are attached on opposite sides, serving both as supports and as electrical conductors for the bulb. The whole assembly then passes through a series of hotter flames, just enough to melt the glass slightly so it seals tightly around the metal parts. A separate machine then bends these copper wires gently according to a preset mold, shaping them into two small hooks that curve inward. Their purpose isn't decorative. They are designed to hold the tungsten filament exactly in the center. Once the bulb's core is assembled, every step is monitored by optical sensors to ensure each glass neck is perfectly formed, accurate down to the smallest fraction of an inch. Installing the filament. Once the glass neck is complete, both workers and automated machines move on to the most delicate stage, installing the filament, the true heart of the light bulb. Along the assembly line, hundreds of tiny support frames glide forward in perfect rhythm, each one holding a glass neck ready for the next step. At a separate workstation, a spool of tungsten wire, a metal capable of withstanding more than 4,000 degrees Fahrenheit, is drawn out and coiled into microscopic springs just slightly thicker than a human hair. Using precision magnetic grippers, an automated arm attaches both ends of each tungsten filament to the miniature copper hooks already fixed inside the glass neck. Once secured, sensors check that the filament is perfectly tensioned, so that when electricity flows through it, the wire glows steadily without snapping or shifting out of place. Before the sealing stage, the entire wire assembly is coated with a thin layer of zirconium solution. This protective film prevents moisture damage, slows down oxidation, and extends a filament's lifespan when it operates inside its inert gas environment. Joining the glass body, with the glass neck now complete and the tungsten filament in place, the production line moves to the stage where two glass parts are joined together to form the bulb's full shape. Each neck is secured onto a rotating clamp, while the round glass shell, the transparent body of the bulb, is positioned on the opposite side. Robotic arms then rotate both pieces in opposite directions, guiding the seam through a series of gas flames heated to about 1,600 degrees Fahrenheit. Within just a few seconds, the glass softens and fuses into a single, seamless bond that appears almost invisible. Once the two parts are sealed, a shaping machine adjusts the neck to achieve the precise diameter needed to fit the aluminum base used later in the process. Immediately afterward, the bulb moves into a forced air cooling zone, where chilled gas prevents the softened glass from deforming. Hundreds of bulbs pass down the conveyor, each one now taking on its familiar form. Almost complete, yet still waiting to be vacuum sealed and filled with inert gas before it can shine. Vacuum sealing and gas injection. Once the two glass parts are sealed, the bulb enters one of the most critical stages that determines its overall durability: the removal of air and the injection of inert gas. The goal of this step is to create a completely oxygen-free environment, allowing the tungsten filament to glow without burning, while stabilizing the internal pressure, so the bulb can shine longer and more consistently. Each bulb is placed onto a vacuum pump head lined with a rubber gasket, while the thin exhaust tube at the neck is connected directly to the suction system. The entire process lasts only about 10 to 12 seconds, yet it must achieve a near-perfect vacuum to eliminate every trace of moisture and oxygen. Immediately after, an automated injector releases a measured dose of argon mixed with nitrogen at a precisely regulated pressure, controlled down to each pound per square inch. This gas blend slows the evaporation of the tungsten filament and prevents dark residue from forming on the inner glass surface. Once the correct pressure is reached, a gas torch heats the tip of the exhaust tube to over 1,800 degrees Fahrenheit, melting the glass until it seals completely and traps the inert gas inside. Attaching the aluminum base. After the bulb has been filled with inert gas and completely sealed, the production line moves on to the stage of attaching the aluminum base and completing the electrical connection. Each bulb is fixed upside down on a clamp, with the glass neck pointing downward. A robotic arm automatically installs the pre-shaped aluminum base, which includes a metal shell, an insulating layer, and the standard threaded screw. At the center of the base lies a contact point where electricity will enter the bulb. Two thin lead wires from inside the bulb are then extended outward. One passes to the center hole of the base and is secured with precision heat weld, while the other is soldered to the side of the aluminum shell to close the circuit. Immediately afterward, the base is pressed firmly against the glass neck using high-temperature thermal adhesive, then rotated to check the threading fit against the standard E26 socket. The assembled bulbs then travel along a testing conveyor, where each one is powered on to verify that the electrical circuit functions correctly before moving to the durability inspection stage. Stress testing and quality control. Before leaving production line, every light bulb must pass its most crucial test: the endurance of its tungsten filament. Along the conveyor, hundreds of bulbs are secured into test racks that automatically connect to a power source. The system begins a rapid on and off cycle lasting about 90 seconds per round, simulating real-world use to train the filament under stress. During testing, the current gradually increases from 50% to 120% of the rated voltage. If the filament cannot withstand the load, the bulb instantly burns out and is removed from the line. Once the stress test is complete, each bulb is cooled down and sent through an optical inspection system designed to detect cracks, discoloration, or areas where the glass may have shrunk due to excessive heat. How LED bulbs are made. As the final incandescent bulbs roll off the line, their warm, golden glow feels like a tribute to more than a century of history. Yet inside today's modern factories, a new generation has already taken their place: the LED bulb. It uses semiconductor technology to produce brighter, longer-lasting light while consuming only a fraction of the energy. But have you ever wondered how these modern lights are actually made? Let's explore that journey right now. Creating the aluminum heat sink. Unlike incandescent bulbs, LED lights don't need a vacuum or inert gas. What they do require is exceptional heat dissipation to protect the tiny light-emitting chip inside. That's why the process begins with solid aluminum bars, which are fed into high-pressure casting machines to form the bulb's body frame, complete with its signature cooling fins. Next, the aluminum housings are turned, drilled, and polished to create perfectly smooth surfaces that help transfer heat efficiently from the LED chip to the outside. A layer of electrostatic paint in silver or dark gray is then applied to prevent oxidation and enhance light reflection. Finally, workers install an insulating ring at the neck and inspect every piece using optical cameras to ensure there are no cracks, scratches, or thread deformities before the next stage begins. Molding the plastic diffuser. Following the aluminum heat sink body, the light of an LED bulb would not be complete without its diffuser, a dome-shaped cover made of polycarbonate plastic that softens and evenly spreads the light. The process begins with tiny, transparent plastic pellets poured into a hopper, gradually feeding into a heating chamber that reaches about 500 degrees Fahrenheit. Within seconds, the material melts completely and is injected into molds shaped like hemispheres or ellipses. The injection pressure stays around 2,000 pounds per square inch, ensuring the molten plastic fills every contour without trapping air bubbles. Over the next 20 to 30 seconds, a forced cooling system stabilizes the structure, preserving the dome's clarity and mechanical strength. When the mold opens, a robotic arm carefully removes each diffuser and places it onto a conveyor for visual inspection, where cameras check for transparency and surface scratches. Some versions receive an extra layer of ultrafine light diffusing coating on the inner surface, which softens the brightness and distributes it more evenly, especially when viewed directly. By the end of this stage, hundreds of gleaming plastic domes are neatly arranged on trays, ready to be assembled with the aluminum body and LED circuitry to form a complete bulb housing. Mounting the LED chips. Inside the component assembly area, hundreds of round, white circuit boards move steadily along the conveyor, each one waiting to receive the seeds of light that will power the LED bulb. The process begins with a precise layer of solder paste printed onto the board surface. It works like an adhesive, holding the LED chips in place during mounting. Moments later, the SMT mounting machine begins its rapid operation. Every second, its robotic arm picks up dozens of chips smaller than a grain of rice and places them exactly on their designated spots, with a margin of error measured in just a few thousandths of an inch. Once all chips are set, the boards enter a reflow oven, where controlled heat melts the solder paste and permanently bonds the chips to the circuit, creating strong and stable electronic connections. By the end of this process, the boards shimmer with tiny points of light, dozens of microscopic LED chips perfectly aligned and ready to be joined with the aluminum heat sink housing to form the luminous core of the bulb. Installing the driver circuit. After the LED circuit boards are completed, they move to the manual assembly area, the stage where human precision still matters most. Here, technicians install the driver, the power converter that allows the LED to operate steadily even when voltage fluctuates. On the workbench, each circuit board is temporarily fixed to the aluminum heat sink body. Using a precision soldering iron, the technician connects the power wires between the LED board and the driver, ensuring every solder joint is bright, round, and perfectly clean. The driver is then placed neatly inside the cavity of the lamp body and secured with screws or thermal adhesive to ensure stable heat transfer. Finally comes the socket, the familiar E26 screw base that lets you twist the bulb into a standard socket. The wires from the driver are soldered to the socket in a quick, controlled weld, and the entire assembly is powered on for an instant test. Final assembly and testing. Once the electrical circuit and aluminum body are complete, the LED bulb enters its final stage, attaching the diffuser cap and undergoing full inspection. Transparent polycarbonate domes are automatically picked up by robotic arms and placed precisely on top of each bulb. A thin ring of heat-resistant silicone is evenly applied along the edge, and the robotic arm gently rotates to press the dome tightly against the aluminum frame, ensuring a perfect seal that blocks out moisture and dust. On some production lines, a heat press system fuses a plastic dome and aluminum body slightly together, creating a durable, permanent bond. After a few seconds of curing, the bulbs move through a light testing conveyor, where optical sensors measure brightness, diffusion, color tone, and light stability. If the illumination spreads evenly without glare or flicker, the bulb advances to the automated packaging area. Here, robotic systems place each bulb into anti-static trays, wrap them in protective sleeves, and print QR codes along with production batch numbers on the packaging. Finally, sealed boxes are stacked on pallets and sent to storage, marking the completion of production journey that powers one of the most reliable and widely used sources of light in the modern world. From glowing glass tubes to LED chips smaller than grains of sand, the journey of a light bulb is proof of how humanity transforms energy into light and technology into everyday endurance. The incandescent bulb gave us our first artificial glow, while LEDs have carried that legacy forward with unmatched efficiency and lifespans that stretch into tens of thousands of hours. Though their shapes have evolved, the mission remains the same: to light the world in smarter and more sustainable ways. If you found this process as fascinating as we did, don't forget to hit like, share this video with your friends, and subscribe to the channel for more deep dives into the incredible manufacturing journeys shaping our modern world. Drop a comment and tell us what production process amazes you the most.